Hello and welcome to this episode of Lutra TV. Today I'm talking with Matt Savage, founder and principal engineer at Apex Water. In today's episode, we're going to be talking about MABRs. So Matt, what is an MABR?
So an MABR is a water treatment membrane, but unlike most water treatment membranes where we're essentially using the membrane as a filter and we're passing water through the membrane, keeping all the solids and contaminants and bacteria on the other side, in an MABR, it's more of a biosupport media. So it's a membrane that we actually grow bacteria on. And instead of pulling water through the membrane, in order to filter the water, we're putting air through the membrane. So it's a hollow fiber. We put air through the inside of the membrane. It diffuses out and you get an oxygen-rich environment on the outside of the membrane, which bacteria love. So bacteria will automatically start growing on the outside of that membrane and form a biofilm, which is excellent for treating water with. So those bacteria then take the oxygen that's coming through the membrane and they use that to primarily remove nitrogen from the water. And also they can remove BOD at the same time.
So within a treatment process, where would this sit? So if you're thinking from your intake through to where you go into your distribution network, at what stage would you see an MABR sitting?
Because there's lots of fibers, we don't want solids, so it's always after the headworks, so we need to screen to a fairly fine level similar to a membrane bioreactor. And so after the headworks, but before the main biological treatment plant. Essentially, it takes the place of your first anoxic tank. And one of the advantages of that is usually we've got all the raw feed and food coming into the anoxic tank and we're recycling some nitrate for it to do its job. And in that environment, there's lots of carbon, there's lots of sugars and fats and things from the wastewater. So what doesn't happen is you can't remove ammonia in the presence of all those carbons because the bacteria go, oh, carbon, sugar's way easier to eat, I'll eat that instead of the ammonia. What we get with this one is we can get both happening in the same tank. So we have oxygen inside the fibers, and that's diffusing out to the biofilm. Ammonia is really small, so that can actually travel into the biofilm and get to where the oxygen is and react. So we get ammonia being removed preferentially. Then the nitrate that's made from that ammonia comes back out through the biofilm, and we're in an environment with lots of food, lots of carbon, and it denitrifies, which is what the the anoxic tank would have been doing in the first place.
Yeah. And so I guess if you're looking at different types of plants, particularly around New Zealand, for example, we have a large amount of oxidation ponds around the country. Is this something where you could actually put this as a side stream process? Is this a primary process? Like, how would it kind of retrofit onto existing plants versus new plants?
Very suitable as a side stream, and especially as an intermediate stage between if someone's got an oxidation pond 1 and an oxidation pond 2, an intermediate stage to polish the rest of the ammonia out of that discharge. Because in New Zealand, one thing our oxidation ponds tend to be very bad at is removing ammonia. So this will boost that ammonia capacity. A lot of other plants like MABRs, moving bed bioreactors, you really want to get that carbon out first or it's not going to work very well. This one, you could put it at the front and it's still going to work, or you could put it between your ponds and it's still going to work.
Okay. And so I guess a little bit more around the technology itself. And look, we've got one membranes behind us here. Do you maybe just want to walk us through that in terms of the membrane structure and I guess some of the pros and cons against that in terms of maybe more that maintenance angle?
Yeah, the cons really, it's the same cons as any membrane system in wastewater. You've got membranes that can block up because you're building biofilm on the membrane. If you feed it lots, that can get a bit out of control and it can become a big sludgy mess. So it's very important we get the cleaning processes right. So there's intermittent scouring happens, so this air gets blasted over the membranes from below to knock the surplus biofilm off. And you can actually control that to get the thickness of biofilm you want with the frequency and intensity of that. So that's one of the disadvantages. Cost, obviously, the capital cost is quite high compared to a lot of traditional processes. Now that there's multiple suppliers in the market, that capital cost is coming down quite substantially where it's becoming quite a competitive technology. Benefits, there is a ridiculously small power use for these things. So the sort of treatment plants that we're building up around the 10 megalitre a day, we're used to talking in thousands of cubic meters per hour of air to do the aeration job and to remove the ammonia. For one of these things, each module, this is a sample beside us. So this is about a 56th of a module. So normal modules about 56 times this big. They use 14 cubic meters per hour of air each. And a relatively small number of those, 20, 30 modules, can do a lot of the treatment of a 10 megalitre plant. So you're talking about orders of magnitude less air and therefore power demand to do that treatment.
So I guess the flip side to that higher OPEX cost then is it capital cost, is it then that lower OPEX cost off the back of this? So, expensive upfront, but over the lifetime of the unit, you're reducing that OPEX?
Absolutely. And they're very, very robust because you're doing all your nitrification and your denitrification in the same tank. It's a lot more resilient to upset, short of actually having contaminants come in that are going to block up the membranes entirely. It's a very, very robust process. The other really good application for it, and overseas this has been the main application of it, is process intensification. And we all know about this in New Zealand. Your treatment plant's struggling. Usually the first thing you struggle to remove is ammonia because that's the first thing that gives up the ghost when your plant's overloaded. You can take your existing anoxic tank at the start of the plant, drop these in without even turning the process off so they hang from above. So you can just drop them in the top of the tank. They hang from above and massively boost. So you could easily add a 20-30% boost to the nitrification capacity of an existing plant just by dropping these modules in. And as soon as you're not talking about new concrete structures, new civil works, your overall project for an upgrade, they become very, very enticing.
Yeah. I guess I'm just kind of sticking with that capacity issue there. I mean, I know with a lot of plants around the country where capacity can be constrained is where they get trade waste or shock loads like that. How does a technology like this deal with, that kind of trade waste load coming in and the more nasty as opposed to your standard municipal waste?
Yeah, one of the quotes I've heard regarding these is that when the going gets tough, the tough gets going, the old cliche with these ones, that we talked about how the ammonia diffuses through the biofilm to get to where it does its job. Diffusion is a process that's limited by the strength of the wastewater around it, the amount of ammonia. So the more stuff goes in, it actually diffuses faster and works harder. So it actually works much better in a stronger environment, which is one of the reasons we always put at the start of the process. So in that regard, it's a huge advantage and it makes your system a lot more stable, especially if it's being put in the front of an existing plant. It takes a lot of those spikes and smooths out what goes through to the rest of the process. So the rest of the process stops seeing those spikes that were probably upsetting it beforehand and becomes a lot more stable, giving you a net better result overall. There have been examples we've seen where there's been a really bad trade waste event. So a winery or something dumping a heap of lees to trade waste and comes through, hits the membranes and just blinds them. So that can happen with any membrane system. That's always going to be a risk. So there's going to be events you can't handle. And that sort of pointed us towards, there's two ways of doing the treatment. You can just have the MABRs or you can have them as a first stage to a further treatment. And having them as a first stage to a further treatment gives you sort of the resilience of both worlds. If the MABR is blind, then you've still got a treatment plant behind it that'll run less efficiently but still do the job. And similarly, suspended growth systems can fail, get bad bacteria growing, and the MABR can pick up the load when that fails.
Yeah. So I guess, and we spoke a little bit around it before with the comparison to MBBR. Within, the wider kind of wastewater technologies and particularly these membranes, what are some, comparisons, let's say, in MBR?
Yeah, so MBR and MABR are very complementary to each other. So the MBR we're putting at the back of a treatment plant to filter the solids out, essentially combine tertiary treatment into your traditional system and replace the clarifier. And the other thing the MBR does is it brings the solids level up in the reactor. So by taking basically all of the bacteria out of the discharge and put them back in, you've got more bacteria to treat your water. So that can both do the similar effect where you can intensify the ability of a given size plant to treat more wastewater, because if you've got twice as many bugs held in the plant, you can treat twice as much water through it. And with the MABRs in the front of that same plant, you get the double benefit that having twice as many bugs floating around the MABR membranes, you can boost your denitrification that happens in that front tank. And you can actually get a lot of your treatment done in the front tank of the plant.
So within these, and again, kind of referencing the unit behind me here, you said, that's 1/56 the times size. I guess in terms of these plants and in terms of these membrane modules, what kind of capacities are we seeing we're treating? Are we looking at just small units? Are we looking at 10 megalitres per day? What's your typical kind of treatment? And
the minimum size module is probably suitable for a 100 cube a day to 150 cube a day plant. So the other item in the background behind us is a package MBR plant. So, for example, we've done exactly the same thing. So one module of the MABR turns a 100 cube MBR package plant into a 150 cube MBR package plant just by giving that extra biological capacity. So that's sort of the very, very small end of it. The one behind us is a demo, so it doesn't count. And an example of that would be, we've just put them into Mary. Mary is a 250 cubic day nominal plant, and it's got 2 modules gone in it to take a lot of the load and enable it to, essentially at the moment, peak flows at Mary can bypass around an MBR plant through the traditional pond system. This would enable much more to be taken through the actual treatment plant.
Yes. So I guess, and kind of linking to that, mention around the package plants and things like that, I guess with New Zealand, like I said, we do have a lot of oxidation ponds, and that's kind of a concern there. So I guess it's quite an interesting angle to look at this type of technology and how that might be retrofitted to plants alongside others where appropriate, like the MBBRs. And again, the whole idea behind that is we have, I guess, quite a high level of non-compliance in New Zealand. So I think just seeing these kind of technologies come out and I guess the ability that they are getting accepted by many helps lift that entire game. And I think as the wastewater environmental performance standards come in, again, these technologies become a lot more relevant as people try to meet those tighter kind of specifications.
Absolutely. And there's sort of 2 ways of looking at that. So we talked earlier about the side stream approach, where we take a portion that's going through the pond, we treat it and recirculate it, or we take some of what's gone through the pond, we treat it better and put it back in. The alternative approach is the likes of what's being done at Ngarawahia and Huntly at the moment, where the cost of these systems is coming down so much, and the advanced technologies like the MABRs are making the plants so small that the approach is actually to completely do a full-scale build of a new plant beside or even reclaiming part of it on the pond and put it through the new plant and use the pond as surge treatment. Because particularly with the membrane bioreactor membranes, they're very flow limited. If you design a 10 megalitre plant, there's no guarantees you're going to get 11 through it. So you really need that flow balancing, and the ponds that are traditionally there are great for that. And the costs of those, even those full treatment systems, are coming down so much that that's actually becoming feasible even for smaller councils. We are only talking about $40 million to do a 10 megalitre greenfield plant.
And I guess that's, again, it's that kind of engineering approach here as well, like say that kind of side stream process, because I&I is still quite a large issue within the country. So it's looking at where those kind of inflows are coming from and where those wet weather events are. And I guess in that kind of same realm, if you can avoid maybe non-treated discharges and things like this by actually pushing in some of that, using that as your surge around the side and then doing that tertiary treatment, I think that's another angle that helps kind of lift the game in the country. So
very, very much so. And the other really good application we've found for these is cold climate. So down south and the likes, when we're growing bubbles, when we're growing bacteria in a tank and blowing bubbles, when you get down below 7 to 5 degrees Celsius, the whole system starts falling over, the flocculent bacteria start falling apart and they don't settle anymore, and everything stops working. The nitrification stops working down around that temperature as well. What's been found internationally is that growing the bacteria on something like a fibre or even an MBBR media, you can actually keep nitrifying down to a lower temperature. And so the 2 things that help are growing on a surface and high oxygen content. So this achieves both very, very well. That you get a very, very high oxygen level in your biofilm, and it's growing on the surface, so you get nitrification down to very low temperatures.
And I think that's been like, I guess, Lutra's direct experience with MBBRs as well around that, which is, again, growing on that media, getting the aeration grids right, and then seeing those kind of work down to those lower temperatures and still continue to operate. So, yeah. Excellent. Well, hey, look, I just want to say thank you for taking the time to talk us through that. I think it's been a really good introduction to the technology and where it kind of sits. So, yeah, look, thank you very much for that. And if you want to know more, feel free to reach out to the team at Apex Water, or follow us and subscribe to our Lutra TV channel.